Alright, welcome back. So today we are going to look at redox stoichiometry. So basically we are performing stoichiometry calculations with our redox reactions. Now of course this has many applications in chemistry and industry and of course in laboratory settings. So this is kind of used almost everywhere, as you kind of remember from Chem 20 with stoichiometry. A lot of it is just trying to calculate either how much will be formed or how much you actually need. So it's kind of used in chemistry everywhere and in industry and laboratories. So that's why we're going to be focusing on this today. Now the process for solving stoichiometry problems, we have our 4 steps right here. Now this is the same that you would have had in Chem 20. So we have step 1, writing out the complete balanced chemical equation. Now in this one right here, because we are dealing with redox chemistry, we will need to use the 5-step method. So there is multiple steps within step 1, but as long as we get our balanced chemical reaction first, we're fine. Now step 2 is determining the number of moles of our given substance. Now normally we're going to be dealing with a lot of stuff in solutions, so for the most part we're going to be given N is equal to V times C, volume times concentration, but we might also need to use number of moles is equal to mass over molar mass if we're given that bit of information, so a mass of something. Now step 3 is still the same. We determine the number of moles of our required or our wanted substance using the mole ratio, and our mole ratio is the number of moles or the coefficient of our wanted over our given. And then of course our final step, convert the moles into a volume using V is equal to N over C, into a concentration using N over V, or a mass using number of moles times molar mass. So it's just kind of depending on whatever the question is asking. We're going to have to use probably one of these equations to solve. And for the most part, this is all we're going to be sticking with for right now. Now for redox, or the stoichiometry that we're going to perform, mostly is going to be a laboratory experiment. For the most part, a titration. So for those of you it's been a while since you've done titration. You can always YouTube some videos on titrations, what they are, to refresh your memory. But we've done a titration analysis at the beginning of the school year as well, kind of getting set up for this. So what a titration is of course we use volumetric analysis. So we use volumes of an unknown concentration of a solution and of course a known one. So of course our titration involves adding a solution, which is our titrant, from the burette to another solution, which is a sample, which is found in an Erlenmeyer flask. So I'm going to show you guys a kind of a diagram of how this looks like if you kind of forget what everything is now in a bit. And we're going to keep adding the titrant until an endpoint occurs, and that is the color change. Now normally with titrations we repeat until we get 3 trials within 0.1 milliliters of each other. So we do multiple. Now depending on the question, we might get one that has multiple things, like the one we're going to look at right here where we have multiple evidence. So we're going to have to find out our 3 best. Or sometimes you'd be given a question like example 1 and example 2 here, where we don't see multiple trials, we just have concentrations and volumes, and we're still going to have to solve. So depending on what type of information is given in the question is going to completely determine on how we solve it. But we'll still kind of tackle that as we get to it. So of course, just remember the endpoint is a sudden change in observable properties. Of course, for us, it's going to be a color change. Now for redox titrations, there's 2 common oxidizing agents we are going to use, and this is because of their strength and their color. So the first one is the permanganate ion, which is MnO4-, and this of course is purple. So of course we can see a direct color change if we add this bright or this really dark purple solution into a reaction and the purple color disappears. Well, we know a reaction occurs, and then as soon as the purple color stays in solution, we know that the reaction's done. So that's why we're going to be using that one, and of course it is a strong oxidizing agent because we have our permanganate almost all the way up at the top here. So it is one of the strongest oxidizing agents that we can use. Now the other one are the dichromate ions, which are Cr2O72-, and these are orange and they turn to yellow. Now this color change is a little harder to detect, so for the most part, even though this is commonly used for a lot of laboratory experimentation, we try not to use it as much because that orange to yellow is a little harder to see. And then of course we see the dichromate is right here in our chart. So once again, it is a very strong oxidizing agent. It's almost right up to the top. So another just definition for titrations, we have the equivalence point. This is a point where the exact theoretical amount of titrant has been added to the sample. So this is only found out, well, we can read it from a graph, but for the most part with these here, it's direct calculation because that is the theoretical chemical amount. And of course, a primary standard. This is something that has high purity and can be used directly to prepare a standard solution. And this is normally a solution that is precisely known concentration. So of course, if you are going to be doing a laboratory technique like a titration, you need to know, for the most part, your titrant, but it could be your sample as well. You need to have one thing within a precisely known concentration, and that is used with a primary standard, and that gives our standard solution. So let's look at our first example. So we will need to follow our 4 steps. Of course, step 1 is balance chemical equation. Step 2 is find the number of moles of our given. Step 3 is going to be find the number of moles of the wanted using the mole ratio. And of course, step 4, solve the question. So we are going to be following these 4 steps to, of course, solve our first question. Now this one right here, this isn't a titration, but it's just kind of a standard redox question that we're going to have to use stoichiometry. So this one's what mass of silver produced, or what is the mass of silver produced when 100 grams of chromium is placed into aqueous silver sulfate? So of course, our balanced chemical equation, step 1, as it said previously, we need to use the 5-step method. So there is going to be a fair bit to do here. So balance equation. So first step in our 5-step method is that we need to write out all the entities in solution. So we have chromium placed in aqueous silver sulfate. So we have chromium solid placed into aqueous silver sulfate. So that means we have Ag plus sulfate SO42 minus. And because it's aqueous, we have H2O liquid. Now from here we need to find our strongest oxidizing agent, strongest reducing agent. So that's when we go to our data booklet, right? And of course and we start scrolling down through until we start at the top left hand side and we start scrolling down to see which one we come across for our strongest oxidizing agent. And we will notice that we have silver is the first one that we see, or our silver ion. So now we can go back. Silver ion is strongest oxidizing agent. So we know we're going to have to use this one, and we can actually write out the half reaction as well if we want to. So that is the half reaction of the silver ion. Now, same in our data book, if we want to find our strongest reducing agent, we start at the bottom right-hand side and start going up until we come across our first substance, which in this case right here, we'll notice we come across chromium solid first. So that means that chromium solid is our strongest reducing agent. So we can take this half reaction and now put it just down below as our strongest reducing agent. And sorry, I'll label the chromium as our strongest reducing agent as well, knowing that the sulfate doesn't do anything and neither does water. So for our strongest reducing agent half reaction, we got chromium solid is producing chromium 2 plus and 2 electrons. And of course, we need to get our redox reaction where we're going to add 2 of these together. In this case right here, we see 1 electron from our silver reaction. We have 2 in our chromium. So we're going to have to multiply our top equation by 2 to get new coefficients in front. And now when we add them together, the electrons cancel out and we get our redox reaction of Cr solid plus 2 Ag plus, which is aqueous, producing 2 Ag solid plus Cr2 plus. Now we did all this for our first step, which is finding our balance reaction. So I know this is a lot of work, but we have step 1 done. Now I'm just going to erase all the work right here just so I have a chance to do the rest, so the last 3 steps here. All right. So I just have this rewritten right here, just erased all that work to kind of get that into balanced chemical equation. And of course, from reading our question, we can tell our chromium solid is our given because we're given 100 grams of our chromium, and it's asking how much mass of silver produced, and of course, that is our wanted here. So our step 2, which is find the number of moles of our given. So because we are given a mass, we go number of moles, in this case right here, it's chromium, is equal to mass of chromium divided by the molar mass of chromium. So the mass given was 100 grams. Now you can check your periodic tables to find the molar mass of chromium is 52.00 grams per mole. And that, of course, is just if you go to your data booklet, go back a few pages to the first little bit, and chromium is right here. So 52 grams per mole for chromium. And of course, when you do that, 100 divided by 52.00, we get 1.9230769 moles. Of course, that is for our chromium. So next we can move on to step 3, find a number of moles of our wanted using the mole ratio. So that is our next step. So from here, we have the number of moles, in this case right here, our wanted, of course, is our silver. Now the equation for this is we take the number of moles of our chromium and we multiply by our mole ratio. And this is why we need the balanced chemical equation, because the mole ratio is going to come from the coefficients of our wanted substance and our given substance. So in this case right here, remember the mole ratio is wanted over given. So we have wanted, which is silver, the coefficient in front is 2. So that is on top, our given is chromium, the coefficient in front is 1. And when we do this calculation, we get 3.8461538 moles. So I'm keeping a lot of digits, of course, as I'm going out with here. You don't need to keep that many if you don't want to. This is just so I make sure I have enough when I'm going through all the rest there. And of course, our last step in our solving, of course, is for solve. Solve the question. So what is it asking? So we go back up and read, and it says what mass of silver is produced. So of course the equation for that is mass is equal to the number of moles times the molar mass. So we take the number of moles we just solved for, so 3.8461538 moles, and we multiply by the molar mass of silver, which once again you just refer back to your periodic table, and you'll find silver is 107.87 grams per mole, and when you plug that in, you get 414.88 grams, and that is just equal to 415 if we want to do 3 significant digits. And that is the answer for that one. So as you can see, as long as you find your balanced chemical equation first, and then of course you follow the rules as is listed up here. Find number of moles are given, find number of moles you want to use the mole ratio to solve. You should be able to solve almost any stoichiometry problem that is thrown your way. So all the stoichiometry problems will have these 4 steps, no matter what. And of course it's just we need to adapt it with finding the number of moles and of course our mass. So the second one, I know I kind of erased it here, which I'm going to go back and do that. So the second one is asking you to determine the volume So this one's a little different where we have concentration. So I'm just going to skip over that one. You can fire up the answer key that's uploaded to Google Classroom and see the answer for that one, but try that one on your own. I just want to move on to the more complex ones, and that's example 3, the more realistic ones where we're using titration data. So this one right here says find the concentration of KMnO4 in a solution, a standardized solution, by titrating 10 milliliters of 0.500 moles per liter of acidified tin 2 chloride with the permanganate. So this 10 milliliters and 0.500 acidified tin is the same. Now, before we even get going, it is handy. Now, we could do it down here if we want to, as writing out the balanced chemical equation, or we can do it in spaces up here as well. Now, before I even start solving the evidence right here, I'm just going to get the balanced chemical equation first. So I can highlight my wanted, highlight my given, and then start going back and solving stuff as needed. All right, so first, step 1 is our balanced chemical equation. Now it says here, draw a diagram of the equipment and label to show the chemicals involved. So before I just kind of get going with the balanced chemical equation as well, this is a general setup, if you remember, for a titration where you have our burette holder right here. This is our burette. Inside the burette goes the titrant. We have our Erlenmeyer flask. Inside the flask goes our sample. Now, from reading here, find the concentration of KMnO4 solution standardized by titrating 10 milliliters. So that means if we titrate the sample, that means whatever's in here, our sample is our tin, was it tin 2 chloride? Acidified is down here, and our titrant, this is our KMnO4. So for our balanced chemical equation, we're going to have to go through our 5-step method again. So that means we write out all of our entities. So we have potassium permanganate. We have acidified tin 2 chloride solution. So that is everything we have right here. So potassium permanganate, acidified tin 2 chloride solution. Now, of course, same thing as before, we're going to have to go to our data booklets, find out our strongest oxidizing agent, strongest reducing agent out of everything that's right here. Now, I know in the original thing when we said stuff is like label everything as oxidizing agent or reducing agent, you can do that, or you can kind of do the quick route, and that is just start at the top left to find your strongest oxidizing agent. You'll notice, like, okay, right here we see acidified permanganate. Awesome. Now, obviously, this is going to be my strongest oxidizing agent. So I can go back to the notes, highlight 2 of these here, strongest oxidizing agent, and I can write out my half reaction like this. Oops. It's not 5 hydrogens. It's 8 hydrogens. So that's our strongest oxidizing agent. Now for our strongest reducing agent, we can go back to our data booklet and do the exact same thing, where we start at the bottom right-hand side and we start going up until we find our first thing that is listed there. And then, of course, when we actually go through it, our tin is going to be the first one that we come across. And the half reaction is written as so. So we got tin 2 plus producing 2 electrons and tin 4 plus. And we have that reaction. Now, of course, we will need to get our redox by making sure the total number of electrons transferred equal out. So in our top equation, we have 5. Our bottom equation, we have 2. So the lowest common multiple here is going to be 10. So I'm going to have to multiply my top equation by 2, multiply my bottom by 5. And what we're left with, our redox equation, we are going to get 2 MnO4 minus plus 5 Sorry, that's a bad looking 5. Just let me fix that up there. 5 SN2 plus 16 H plus produces 5 Mn2 plus 5 SN4 plus, and then plus our 8 H2O. So that is our redox reaction. And of course, from here, we can highlight our given and our wanted. Now, how we figure that out is we figure out what we have more information for. Now, up here, we have titrating 10 milliliters of 0.5 moles per liter acidified tin 2 chloride. So where we have two things right here, obviously it's our given, but it's also saying find the concentration of KMnO4. So we know just from reading the question, this is going to be our wanted, and this is our given. All right, so that is all that work just for the balanced chemical equation. Now what I'm going to do is go back and actually fill in the chart and everything like that, just so I have all the information I need for my wanted and my given. But before that, I'm just going to erase the work for my balanced chemical equation and just have it up here so I can just start going with the information that's written down there. So I'm just going to move all that up here now. All right, so I have that just kind of moved up there. And that is, of course, our step 1, our balanced chemical equation. Now our step 2 is still going to be find the number of moles of our given. In this case right here, it is our tin 2 chloride. In this case right here, just tin. So what we have is 10 milliliters. So remember, this has to be in liters because our concentration in moles per liter. So that is just 0.0100 liters, right? We divide by 1,000. So the equation that we have for number of moles is equal to C times V. So we have our concentration of 0.500 moles per liter times our liter, 0.0100 liters. And we are left with, in this case right here, 0.00500 moles. So our next step, step 3, find the number of moles of our wanted using our mole ratio. So of course that is number of moles, in this case right here, of MnO4 minus is going to equal number of moles of our tin times our mole ratio. And that is equal to what we just solved, 0.00500 moles. And our mole ratio is wanted, so 2 over given 5. And then we are left with, in this case right here, 0.00200 moles. Now finally, our last step, step 4, is solve. Now this one's asking for volume, or sorry, it's concentration. So concentration is equal to number of moles divided by our volume. Now of course, our number of moles we already have. Sorry, I should be keeping the color the same here. We have 0.00200 moles divided by, now the volume. Where can we find the volume? Well, now this is where I'm actually going to look at this evidence. Now you could have filled this in and done all the calculations earlier, or you can just do it right now when you actually need it. So what we have right here is the different trials. So you have initial, final volume, initial volume, and of course volume of KMnO4 added. Now of course, in order to get these numbers right here, we just subtract every single one. In this case right here, when we subtract 18.40, subtract 1, we get 17.40. And we do the same for each one here, and we get these numbers. Now of course, there's 4 trials here. Now on the previous page it said we only use the best 3 examples. So in this case right here, it said we try to get 3 within 0.1. If the information has that or it doesn't have that, then that's it. But we'll notice that it's 16.9, 16.8 are 0.1 from each other, and then 16.8 and 16.7 are 0.1 from each other, and then that 17.4 is nowhere even close. So we're going to take all this and omit that data. And what we're going to do is get the average volume is equal to, well, we go 16.90 plus 16.70 plus 16.80, all divided by 3, and we get the average to equal 16.80 milliliters, or 0.01680 liters. And this, of course, is the volume of our potassium permanganate. So now we can take this value down here, add that to get our answer. The concentration of the permanganate is 0.119 moles per liter. And that is how we are going to solve all of our titration analysis questions. So just remember that we have our 4-step method, right? Balance the equation, find the number of moles you're given, find the number of moles you're wanted, and then of course solving the question. And of course, if you are given your data table like this, once again, you can solve everything in the one shot, or you can only just solve the data table when you need it. And of course, in this case right here, I didn't need the volume of permanganate until I was down in my last step of solving the question. So that is how we use our information to kind of solve redox titration questions. Of course, your best bet right now is to open up your workbook and try to do as many of these as possible. Get familiar, and of course, do not forget the whole thing with the Buretin titrant and everything like that. Sadly, we won't be able to do anymore unless we do get back into a classroom at some point soon. But if we don't, just try to watch a video and try not to forget the titration stuff. But either way, so this is kind of it for this week. Next week, we're going to be looking at electrochemical cells. So good luck, and of course, make sure to email me or contact me if you guys have any questions. So see you guys next